Welcome to Section 11.1, Part 1. This is the 102nd session of the CISSP Exam Prep series. In this session, we'll unpack the reference model that describes how two machines talk. We'll answer several questions. Why was this model created in the first place? How do the 7 layers fit together? How does data get wrapped and unwrapped as it moves? What is the network container called at each stage? And what do the top 3 layers actually do? Why does this matter beyond the exam? Because this model is the shared vocabulary of every network conversation you will have. Imagine a vendor tells you there are appliance filters at layer 3, or your team argues whether an outage is a cabling fault or a session problem. Without a mental map of the layers, you are guessing. With one, you place the problem instantly and route it to the right control. So why was this reference model created at all? Rules that govern how data crosses a wire are called protocols. Early on, every vendor built its own, and their gear refused to cooperate. A standards body designed one shared blueprint so systems from different makers could interoperate. Treat it as a theoretical ideal, not a literal build. It describes how communication should work on perfect hardware, and it became the common reference everyone points to. How do the 7 layers fit together? The model splits the whole job of communication into 7 stacked layers. Each layer owns one narrow set of tasks and nothing more. A layer only ever talks to the one directly above it and the one directly below it. Picture an assembly line where each station does a single step before passing the work on. Data flows down the stack on the sending side and back up on the receiving side. How does data get wrapped as it travels down? Through a process called encapsulation. As your message descends, each layer adds its own header and sometimes a footer around what it received from above. The whole bundle from the layer above simply becomes the payload of the layer below. On the far end, the reverse happens, and each layer peels off its own wrapper. That unwrapping is called de-encapsulation. Why can only the matching layer read each wrapper? Because each header is a private note between peers. The information one layer adds, its checksums and instructions, is meaningful only to the identical layer on the other machine. We call that peer layer communication. Think of 2 departments exchanging sealed memos through the mailroom. Only accounting opens the accounting envelope, no matter how many hands it passed through on the way. What is the network container called at each stage? Its name changes as it descends. At the top 3 layers, it is simply a protocol data unit. At the transport layer, it becomes a segment, or a datagram if the connectionless protocol is used. At the network layer, it is a packet. At the data link layer, it is a frame. And at the physical layer, it is nothing but bits on the wire. Learn these names, because the exam uses them to tell you which layer it is testing. What does the top layer, the application layer, actually do? It is the doorway between your software and the stack. The program itself does not live here. What lives here are the protocols and services that let software transfer files, exchange messages, and reach remote systems. Think of it as the reception desk of a building. It does not do the work inside, but nothing gets in or out without passing through it first. So let's bring it together. This reference model was built so different vendors could interoperate around one shared blueprint. 7 layers each own a slice of the job, talking only to their neighbors. Encapsulation wraps data on the way down, and de-encapsulation unwraps it on the way up. With each header readable only by its peer. The container is named differently at each layer, from protocol data unit down to raw bits. And the application layer is the doorway between your software and the network. In Part 2, we walk down through the remaining layers. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 11.1, Part 2. This is the 103rd session of the CISSP Exam Prep series. We pick up the walk down the stack where the last part left off. In this session, we'll work through the lower 6 layers and the gear that lives at each one. We'll answer several questions. What does the presentation layer handle? What does the session layer manage? What does the transport layer guarantee? What does the network layer decide? What does the data link layer stamp on each frame? And what happens at the physical layer? Why does this matter beyond the exam? Because every network control you deploy attaches to one of these layers. Suppose you are hardening a branch office. Your encryption choice, your routing rules, your switch settings, and your cabling all belong to different layers. When you can name the layer a device operates at, you know exactly what it can and cannot see, and where to place the defense. Let's set the scene before the detail. The lower layers each own a specific job on the journey from software to signal. Formatting, dialogue, delivery, routing, framing, and finally raw transmission. On modern networks that run the Internet Protocol suite, a couple of these layers have no separate existence and their work is folded elsewhere. Keep that quirk in mind as we go, because the exam loves to test where those duties actually land. What does the presentation layer handle? It is the translator. It reshapes data into a standard format any compliant system can read, imposing common structure and formatting. It is also where encryption and compression traditionally sit. Here is the catch. On Internet Protocol networks, there is no real presentation layer, because reformatting for transport is rarely needed. Encryption still happens, just in other places, such as before data enters the stack, at the transport layer, inside a VPN, over wireless, or in bulk at the physical layer. What does the session layer manage? It is the conversation coordinator. It opens, maintains, and closes the dialogue between two machines, sets checkpoints so a broken exchange can resume, and decides the direction of flow. That direction comes in three modes. Simplex is one-way only. Half-duplex is two-way, but only one side at a time. Full duplex is two-way at once. And again, on Internet Protocol networks, there is no distinct session layer. Those duties get handled by the transport protocol, or not at all. What does the transport layer guarantee? It manages the integrity and control of the connection. It establishes a logical link between two nodes and defines the rules of the session, how big each segment can be, how integrity is checked, and how lost data is spotted. It handles sequencing, error checking, flow control, and multiplexing. Think of it as a shipping manager who numbers every carton, confirms each arrives, and reorders whatever went missing. Its main occupants are the reliable transport protocol, its lightweight, connectionless cousin, and transport layer security. What does the network layer decide? It handles logical addressing and routing. Logical addressing means an address assigned by software rather than burned into hardware, and the header here carries the source and destination IP addresses. This layer chooses the path but does not promise delivery. The device that rules this layer is the router. A router reads the destination IP address and picks the best path by speed, hop count, and preference, using its routing table. Picture a dispatcher choosing the fastest route for each delivery truck based on live traffic. What does the data link layer stamp on each frame? The physical hardware address. This layer formats the frame for the specific network technology, such as Ethernet, and adds the source and destination MAC addresses. A MAC address is a 48-bit hardware address written in hexadecimal, and its first half identifies the manufacturer through a registered vendor code. Because that code is tied to the maker, some devices can be recognized by their MAC address alone. The gear here is the switch, which forwards each frame out the correct port based on its destination MAC address. What happens at the physical layer? Everything becomes signal. This layer converts a frame into bits for transmission over the medium and turns arriving signals back into bits. There is no logic about meaning here, only electricity, light, or radio. The devices that live here are the humble ones: network cards, hubs, repeaters, and amplifiers. A hub blindly copies a signal out every port, and a repeater simply boosts a signal so it can travel farther down the wire. So let's bring it together. The presentation layer translates, encrypts, and compresses, though the Internet Protocol suite scatters those duties. The session layer runs the dialogue in simplex, half-duplex, or full duplex, and likewise has no separate existence there. The transport layer guarantees the connection with sequencing and error control. The network layer routes by logical IP address, ruled by the router. The data link layer stamps hardware MAC addresses on frames, home to the switch. And the physical layer turns frames into raw bits, home to cards, hubs, and repeaters. Map any control to its layer and you always know what it can protect. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.2. This is the 104th session of the CISSP Exam Prep series. In this session, we'll look at the model that actually runs the internet. We'll answer several questions. What is this 4-layer model, and how does it map to the 7-layer reference model? Why does its naming overlap cause confusion? And why is a protocol suite this popular also so exposed to attack? Why does this matter beyond the exam? Because this is the stack your traffic really travels on, not the idealized one. Imagine you are reviewing a firewall design or reading an incident report. The names of these layers show up everywhere, and so do the classic attacks against them. Knowing the model and its weak points lets you read those documents fluently and anticipate where trouble comes from. So what is this 4-layer model? It is the practical stack that grew out of the Internet Protocol Suite itself. Instead of 7 layers, it uses 4. From top to bottom, they are application, transport, internet, and link, though each carries a few alternate names. It was actually built before the 7-layer reference model existed. Picture a car that was already on the road before anyone drew the official engineering diagram. The vehicle came first, the textbook came later. How does this model map to the 7-layer one? Its 4 layers absorb the same work the reference model spreads across 7. The application layer here covers the top 3 reference layers at once, folding in presentation and session duties. Transport lines up with transport. The internet layer matches the network layer. And the link layer covers both data link and physical. Think of 2 maps of the same city, one drawn with 4 districts and one with 7 neighborhoods. Same streets, different groupings. Why does the naming overlap cause confusion? Because the 2 models share several layer names and people swap them freely. Someone says transport layer, but which model do they mean? The safe habit is a default. Unless you are told otherwise, assume the 7-layer reference model, since it is the more widely cited teaching standard. On the exam, read the context first, then decide which map the question is using before you answer. Why is a protocol suite this popular also so exposed? Because it was designed for ease of use and interoperability, not for security. The suite is platform independent and built on open standards, so it runs on nearly every operating system, but it is heavy on resources and relatively easy to attack. Poorly built implementations open the door to a long list of classic threats: buffer overflows, connection flood attacks, various denial of service attacks, fragment and oversized packet tricks, spoofing, adversary in the middle interception, and session hijacking. It is like a house designed for easy access, where every convenient entrance is also a way in for an intruder. Are there quieter attacks too? Yes, and they leave no footprint. This suite, like most protocols, is open to passive attacks through simple monitoring or sniffing. An eavesdropper does not break anything or trigger an alarm. They just listen, capturing traffic as it flows past, and read whatever was not encrypted. That is why encryption matters at every layer. If the data is readable on the wire, a silent observer already has it. So let's bring it together. This is the 4-layer stack that actually powers the internet, and it predates the 7-layer reference model. Its 4 layers map cleanly onto the 7, just grouped differently, with the application layer swallowing the top 3. Because both models share layer names, default to the reference model unless told otherwise. And because the suite was built for convenience over security, it invites a wide range of active attacks and quiet, footprint-free sniffing. Know the map and know where it leaks. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.3. This is the 105th session of the CISSP Exam Prep series. In this session, We'll learn how professionals actually look inside network traffic. We'll answer several questions. Why analyze traffic in the first place? What tool captures and decodes it? How does a capture card grab everything on the wire? How do filters keep the flood manageable? And how is machine learning changing this work? Why does this matter beyond the exam? Because reading traffic is a daily reality in operations and incident response. Imagine an application keeps timing out, or you suspect data is quietly leaving your network. Capturing and studying the packets is often the fastest way to see the truth on the wire. But the very same skill is what an attacker uses to spy on your conversations, so you have to understand both sides. So why analyze network traffic at all? Because it is how you understand what your network is really doing. Analysis helps you trace malicious communications, spot errors, and fix transmission problems. It is a core part of running a healthy network. But the same technique has a dark twin. Eavesdropping on traffic can violate confidentiality and serve as the reconnaissance phase before a bigger attack. The tool is neutral. Intent decides whether it defends or invades. What tool captures and decodes traffic? A protocol analyzer. It can be dedicated hardware or software running on an ordinary host, and its job is to capture frames and packets and store them for study. Once captured, traffic can be examined by hand or with automated scripts. Here is a useful distinction. A plain sniffer just grabs packets, while a true protocol analyzer decodes and interprets what is inside them. It passes each header into a readable outline and shows the payload in both hexadecimal and plain text. Think of it as an X-ray machine for network conversations. How does a capture card grab everything on the wire? By switching into a special listening state. Normally, a network card ignores traffic not addressed to it. To capture everything on the local segment, the analyzer puts the card into promiscuous mode. In that state, the card stops filtering by destination hardware address and scoops up every frame that reaches the interface. Picture standing in a busy hallway and choosing to listen to every conversation, not just the ones aimed at you. How do filters keep the flood manageable? With two kinds of filter applied at different moments. A capture filter is a set of rules that decides which frames get saved into the file and which are thrown away as they arrive. A display filter works later, showing only the saved frames that match what you are hunting for. One controls what you keep, the other controls what you see. Together they turn an overwhelming torrent into a focused view. Analyzers range from simple capture tools to fully automated engines, and both open source and commercial options exist. How is machine learning changing this work? By handling a volume of traffic no human can read. Modern networks generate far too much data to watch packet by packet, so machine learning systems for network detection and response step in. They learn what normal behavior looks like, then flag anomalies without depending only on fixed signatures. That helps them catch evasive threats, cut down the alert fatigue that wears out analysts, and adjust as the network changes so their models do not drift out of date. Think of a seasoned guard who learns the building's normal rhythm and instantly notices when something feels off. So let's bring it together. Traffic analysis lets you troubleshoot and hunt threats, but the same power enables eavesdropping, so intent is everything. A protocol analyzer captures and decodes traffic, going deeper than a plain sniffer. Promiscuous mode lets a card grab every frame on the segment. Capture filters control what you save and display filters control what you see. And machine learning detection now scales this work far beyond human limits, spotting anomalies and easing analyst fatigue. Master the tool, and you can both defend the wire and recognize when someone is listening in. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.4. This is the 106th session of the CISSP Exam Prep series. In this session, we'll tour the everyday protocols that live at the top of the stack. We'll answer several questions. How should you think about this whole family? Which remote access and file transfer protocols must you retire? How do the email protocols differ? And how do you secure them? What separates plain web traffic from secure? And which management and service protocols round out the set? Why does this matter beyond the exam? because these protocols and their ports are the raw material of firewall rules and hardening checklists. Imagine you inherit a network and find an old service still accepting plain text logins. Recognizing which protocols are safe, which are obsolete, and which secure replacement to reach for is exactly the judgment a security professional applies every week. How should you think about this whole family? As a set of specialized couriers, each with its own job and its own street address. These application layer protocols handle specific tasks, moving files, carrying mail, serving web pages, or reporting device health. Each one listens on a numbered port, its address on the machine. The recurring theme you must internalize is simple. Many of the originals send everything in clear text, and for each one there is now an encrypted successor you should use instead. Which remote access and file transfer protocols must you retire? The plain text ones. The old terminal access protocol sends commands and even passwords in the clear, so replace it with the secure shell. The classic file transfer protocol likewise exposes credentials and data, so move to its secured variants. Its trivial cousin needs no authentication at all and should simply be avoided. Picture mailing a postcard that anyone in the sorting office can read. That is what these legacy protocols do with your login. Swap the postcard for a sealed envelope. How do the email protocols differ, and how do you secure them? 3 protocols do the heavy lifting, and each has an encrypted form. One protocol carries mail from a client to a server and between servers, and you should run it wrapped in transport layer security. 2 more pull messages down into a mail client. The older one simply downloads and removes, while the newer one can sync, fetch just headers, and manage messages on the server. Both should only run in their encrypted forms. The rule holds across all 3. If it is not encrypted, assume someone can read the mail. What separates plain web traffic from secure web traffic? Exactly one thing: encryption. The basic web protocol moves page elements from server to browser in clear text, readable by anyone in the path. Its secure form is the same protocol wrapped in transport layer security, which shields the whole exchange. This is the single most visible example of the pattern we keep seeing. Same job, but one version is a glass envelope and the other is opaque. On any modern site, the encrypted form is the only acceptable choice. Which management and service protocols round out the set? Several that keep infrastructure running. One protocol hands out addressing configuration to devices as they boot, saving you from touching each machine. Others spool print jobs, share files between different systems, or provide a graphical interface to command line systems. And several of these are safest when tunneled inside a VPN. Finally, there is the network management protocol used to collect health and status from routers, switches, and firewalls across your environment. Its early versions sent authentication text in the clear, so insist on the modern, encrypted version. Its status alerts, called traps, notify your console the moment a threshold is crossed. So let's bring it together. Application layer protocols are specialized couriers, each on its own numbered port. The unifying lesson is that legacy plaintext protocols have secure successors, and you should always reach for the encrypted one. Retire the old terminal and file transfer protocols in favor of secure shell and its secured variants. Run all 3 mail protocols and the web protocol wrapped in transport layer security. Tunnel the riskier service protocols through a VPN and use only the modern encrypted network management version. When in doubt, choose the sealed envelope over the postcard. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.5. This is the 107th session of the CISSP Exam Prep series. In this session, we'll get precise about how the transport layer moves data. We'll answer several questions. What is a port and what is a socket? How are the port ranges divided? How does the reliable protocol open and close a session? Why is that protocol considered dependable? And when should you choose the fast, connectionless protocol instead? Why does this matter beyond the exam? Because these 2 protocols and their behavior underlie firewall design, troubleshooting, and attack analysis. Imagine you are reading a packet capture during an incident, or writing a rule that permits one service but blocks another. Knowing how sessions are built, torn down, and numbered by port is what lets you tell normal traffic from something hostile. So, what is a port and what is a socket? A port is a numbered channel that lets one address carry many conversations at once. Port numbers are 16-bit values, which gives 65,536 of them counted from 0. Each simultaneous conversation uses a different port, so a single IP address can juggle many at the same time. Combine an IP address with a port number, and you get a socket, the precise endpoint of one connection. Think of the IP address as a building and the port as a specific apartment inside it. How are the port ranges divided? Into 3 bands, each with a purpose. The first block, the lowest numbers, are the well-known or service ports, reserved for servers offering standard services. The middle block holds the registered ports, claimed by particular software products through the assigning authority. The top block are the dynamic or ephemeral ports, borrowed briefly and often at random by clients as their source port for a single conversation. Picture reserved parking near the entrance, assigned company spots in the middle, and open visitor spaces at the far end of the lot. How does the reliable protocol open and close a session? With a clear handshake and a clean goodbye. To open, the two systems exchange 3 messages. The client sends a synchronized request, the server answers with a synchronize and acknowledge, and the client replies with an acknowledge. That 3-step exchange establishes the session. To close, there are 2 ways. The graceful method uses finish messages to wind the session down politely, and the abrupt method uses a reset message to slam the connection shut immediately. Think of a phone call that either ends with a proper goodbye or with someone simply hanging up. Why is that protocol considered dependable? Because it refuses to give up on missing data. It is connection-oriented and full duplex, and it guarantees delivery. If a window of data arrives incomplete, the receiver sends no acknowledgement, and after a timeout, the sender resends the whole window. It keeps resending until it gets an acknowledgement, or the session is reset, or the application stops, or the power is cut. Use it whenever data absolutely must arrive intact. It behaves like a courier who keeps returning until you sign for the package. When should you choose the fast, connectionless protocol instead? When speed matters more than certainty. This lightweight protocol also lives at the transport layer, but it is best effort and unreliable. It skips sequencing, flow control, and any real error correction, and it never sets up a session first. That gives it very low overhead, so it moves data quickly. The trade-off is that lost data is simply gone. Reach for it only when a missed piece does not matter, which is why real-time audio and video streaming favor it. In a live call, a dropped fragment is better than a delayed one. So let's bring it together. A port is a numbered channel, and an IP address plus a port makes a socket, one precise endpoint. Ports fall into 3 bands, well known for servers, registered for products, and ephemeral for clients. The reliable protocol opens with a 3-way handshake and closes gracefully with finish messages or abruptly with a reset. It guarantees delivery by resending until acknowledged. So use it when data must arrive. The connectionless protocol trades reliability for speed, so use it for real-time streams where a lost fragment is acceptable. Choose the protocol to match what the data can tolerate. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.6. This is the 108th session of the CISSP Exam Prep series. In this session, we'll unpack the naming system that turns readable names into addresses. We'll answer several questions. How do the 3 kinds of address relate? What does this system actually do? And how is a full name built? What lives inside a zone as records? How is the system secured? What attacks poison it? And how do you defend? And what threats target the domain name itself? Why does this matter beyond the exam? Because name resolution is a favorite target and a quiet one. Imagine users at your company suddenly landing on a convincing fake of your banking portal with nothing obviously wrong on their screens. A poison name lookup can do exactly that. Understanding how resolution works and where it breaks is what lets you detect and prevent these silent redirections. So how do the three kinds of address relate? They stack in layers of permanence. The domain name is a human-friendly label, and it is the least fixed. The IP address is a logical address assigned on top of the hardware, and it too can change. The hardware address burned into the interface is the most permanent, though even that can sometimes be spoofed. Resolution walks down this stack. The naming system turns a name into an IP address, and then the address resolution protocol turns that IP address into a hardware address. Think of a name, a mailing address, and a fixed GPS coordinate for the same house. What does this system do, and how is a full name built? It resolves human-friendly names into addresses using a hierarchical naming scheme shared across public and private networks. A fully qualified domain name has three main parts. The top-level domain on the right, such as the common commercial or organizational endings, the registered domain name that an owner claims through a registrar, and the host or subdomain portion on the left. Read it right to left, from the broadest zone down to the specific machine. Picture an address written backwards, starting with the country and narrowing to the exact door. What lives inside a zone as records? Every registered domain has an authoritative name server holding its zone file, a collection of resource records. Each record type answers a specific question. Address records map a name to a numeric address, one type for the older addressing and another for the newer. A pointer record does the reverse, mapping an address back to a name. An alias record links one name to another. A mail record names the servers that accept email for the domain. A name server record identifies which servers are authoritative. And the start of authority record holds the master details and refresh timing. Think of the zone file as the domain's phone book, each record a different kind of listing. How is name resolution secured? With two complementary additions. The security extensions add mutual certificate authentication and encrypted sessions between servers, which blunts server-focused abuses like zone poisoning. But those extensions protect only the servers, not the clients querying them. To protect the client side, resolution over an encrypted web session wraps the query and response inside a protected tunnel. A privacy-focused variant even adds a proxy between client and resolver, so the resolver never learns who asked. The trade-off is that you now trust that proxy provider. It is like sealing both ends of a conversation, not just the switchboard. What attacks poison the system? And how does one work? Poisoning means feeding a client false name to address information so it reaches the wrong system. There are several avenues. A rogue server listens for queries and races to answer first with a lie, and because responses must echo a small query identifier, the attacker simply copies it. Attackers often prefer caching servers, since those are watched only by local operators, so a lie can sit unnoticed for a long time. Related tricks: edit the localhost file, corrupt a client's configured resolver, or spoof the query directly on the wire. The end effect is the same. The victim trusts a poisoned answer and is quietly redirected. How do you defend against poisoning? With layered, practical measures. Run a split arrangement, one server facing the public and a separate one for internal use, so outsiders never touch your internal records. Restrict zone transfers and require internal clients to resolve through your internal servers. Deploy intrusion detection to watch for abnormal lookups, harden every server and client, and turn on the security extensions and encrypted resolution where supported. You can even weaponize the technique defensively with a sinkhole, deliberately returning false answers to steer malware away from its command servers or to block known malicious sites. There is no single patch, because these attacks abuse normal behavior, so detection and layering are the real defense. What threats target the domain name itself? Two stand out. Domain hijacking is the theft of a domain's registration, taking control without the owner's consent, often by stealing registrar credentials. The new owner can then host a convincing fake and harvest personal information from unsuspecting visitors. Defend it with strong multi-factor authentication at your registrar and by keeping registration from lapsing through auto-renewal. The second threat is the homograph attack, which registers lookalike names using characters from other alphabets that mimic familiar letters. To the eye, the name looks legitimate, but it resolves somewhere hostile. Slow down and inspect any address that looks a shade off. So let's bring it together. 3 address types stack, from changeable name to permanent hardware, and resolution walks down them. The naming system resolves hierarchical full names, whose parts read from broad zone to specific host. Zone files hold resource records, each a different kind of listing. Security extensions protect servers, while encrypted resolution protects clients. Poisoning feeds clients false answers through rogue or caching servers, hosts files, or spoofing, and you counter it with split servers, restricted transfers, monitoring, and hardening. And the domain name itself is a target through hijacking and lookalike homograph tricks. Guard the lookups, and you guard where your users actually go. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.7. This is the 109th session of the CISSP Exam Prep series. In this session, we'll get concrete about the protocol that addresses every packet. We'll answer several questions. What does the Internet Protocol itself do? How do the two versions of it differ? How does the newer version hand out addresses? What are the security concerns during migration? How do the classic address classes and modern notation work? And what do the two helper protocols add? Why does this matter beyond the exam? Because addressing decisions shape your filtering, your monitoring, and your attack surface. Imagine your organization begins enabling the newer address version on production systems. If your security tools cannot see that traffic, you have just opened a blind spot. Knowing how addressing works and how the two versions coexist is what keeps that transition from becoming a gap an attacker walks through. So what does the Internet Protocol itself do? It provides root addressing for packets, and that addressing is the foundation of global communication. It gives every packet an identity and prescribes a path. But notice its personality. It is connectionless and unreliable. It does not promise packets will arrive in order, or arrive only once. It simply makes its best effort to find a route, even across a damaged network. That is why you pair it with the reliable transport protocol on top. Think of a determined courier who always tries a route but signs no guarantee. How do the two versions of it differ? Mainly in address size and built-in features. The older version uses 32 bits for addresses, while the newer one uses 128, a vastly larger space. The newer version also brings features the old one lacked, such as scoped addresses for grouping access, automatic configuration, and quality of service priorities for managing traffic. And where the older version treats security as a bolt-on, the newer version has the security suite built in. Picture upgrading from a small numbering scheme that ran out of room to one with practically endless addresses and modern conveniences baked in. How does the newer version hand out addresses? In two ways. Its updated configuration service can run in a stateful mode, assigning specific addresses and tracking them, much like the classic service did. Or it can run stateless, providing configuration details without assigning addresses, leaving devices to build their own. In that self-assembly, routers periodically advertise the network prefix, and each device combines that prefix with an interface identifier often derived from its hardware address. For privacy, some devices randomize that identifier instead. The result is a unique address the device assigns to itself. It is like a building announcing its street, and each resident forming their own apartment number from it. What are the security concerns during migration? Two big ones. First, the enormous address space means attackers have far more source addresses to rotate through, so simple address block lists become much less effective. Second, and more dangerous, is a monitoring gap. If you enable the new version before every security and monitoring product fully supports it, that traffic flows unwatched and unfiltered, effectively a covert channel. Both versions can coexist through a few methods, running both stacks at once, tunneling one inside the other, or translating between them. And a cautious organization can start at the edge, supporting the new version only on internet-facing devices. Upgrade your visibility before you flip the switch. How do the classic address classes and modern notation work? The older addressing was first organized into classes by the value of the first octet. The early classes offered progressively smaller networks, with additional ranges reserved for multicasting and for experimental use. A couple of ranges were set aside for special jobs, such as the loopback address a machine uses to talk to itself. But rigid classes wasted addresses, so the field moved to a flexible system. Classless notation writes the network size as a simple /count after the address, letting you size subnets precisely and combine ranges. Think of switching from a few fixed box sizes to made-to-measure packaging. What do the two helper protocols add? Health checks and group delivery. The control message protocol reports on the health of a network or link, and it powers familiar tools that test whether a remote system is reachable and how well the path performs. Because its features were abused in bandwidth flooding attacks, many networks now limit or throttle it. The group management protocol supports multicasting, the delivery of data to a specific set of recipients at once. It manages which hosts belong to a multicast group, and a single stream can be duplicated at a router only where paths diverge. Think of one announcement copied only at the hallways where audiences split off. So let's bring it together. The Internet Protocol addresses and routes packets on a best effort, unreliable basis, which is why you layer the reliable transport protocol on top. The newer version dwarfs the older one in address space and bakes in features and security. It assigns addresses statefully or lets devices self-configure statelessly. Migration raises real concerns, especially unmonitored traffic, so extend visibility before enabling it. Classic classes gave way to flexible, classless notation. And the two helper protocols add health testing and multicast group delivery, master addressing, and you control both where traffic goes and who can watch it. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.8. This is the 110th session of the CISSP Exam Prep series. In this session, we'll examine a small protocol with an outsized security impact. We'll answer several questions. What does the address resolution protocol actually do? How is its cache poisoned? What is the unsolicited variety of that attack? Can static entries be both a weapon and a shield? And what is the strongest defense? Why does this matter beyond the exam? Because this protocol operates on your local segment with no built-in authentication, which makes it a favorite for interception on the inside. Imagine an attacker who already has a foothold on your network, quietly positioning themselves between two machines to read the traffic flowing between them. This protocol is often how they do it. Understanding the attack is the first step to catching it. So, what does this protocol actually do? It bridges logical and physical addressing. It resolves an IP address into the hardware address that traffic on a local segment actually uses to reach a machine. It works by caching and broadcasting. A device first checks its local cache for the mapping. If it is missing, the device broadcasts a request, and the owner of that address answers with its hardware address, which then gets cached. Think of shouting a name across a room and letting the right person raise their hand so you know where to hand the note. How is its cache poisoned? By an attacker sending falsified replies. Because a device updates its cache with whatever reply it receives, an attacker can simply answer with a lie, mapping a victim's IP address to the attacker's own hardware address. Traffic then flows to the attacker instead of the real destination. A poisoned entry lingers until it times out, usually within a few minutes, and when the victim broadcasts again, the attacker gets a fresh chance to lie. It is like slipping a false forwarding note into the mail room, so mail meant for one desk quietly lands on yours. What is the unsolicited variety of this attack? It is the gratuitous reply sent with no request behind it. Normally, a reply answers a query, but a device can also announce its mapping unprompted. That announcement has legitimate uses, such as announcing a device's presence or supporting reliable failover between redundant devices, but an attacker can abuse it, broadcasting false, unsolicited mappings to poison caches without waiting to be asked. Picture someone walking through an office, loudly redirecting deliveries to their own desk, whether or not anyone requested the update. Can static entries be both a weapon and a shield? Yes, and that dual nature is worth remembering. A third form of poisoning creates static entries locally, which is easily done through a malicious script on the client, though such entries do not survive a reboot. But you can also flip static entries into a defense. A manually fixed mapping will not be overwritten by any incoming reply. The catch is that static entries remove the flexibility a network needs as devices come and go. And because they vanish on reboot, you would need a script to rebuild them each time. So the same technique defends and attacks depending on who sets it and why. What is the strongest defense? Controlling the switch. The best protection is port security on the switch, which can block communication from unknown or rogue devices and detect a system that is answering every request. Beyond that, a local or host-based firewall, a host intrusion detection and prevention system, or dedicated endpoint tools can block unrequested replies and announcements. Purpose-built monitoring tools also exist to watch for this exact abuse. Layer these together, lock the switch ports first, then add host-level detection so a lie on the wire gets caught even if it slips past. So let's bring it together. This protocol resolves IP addresses into hardware addresses using caching and broadcasting, with no authentication to vouch for the answers. That gap lets an attacker poison a cache with falsified replies, redirecting traffic to themselves. The unsolicited, gratuitous reply does the same without even waiting for a query. Static entries cut both ways, serving as an attack or a rigid defense. And the strongest countermeasure is switch port security, backed by host-based detection. Watch this quiet protocol closely, because it is often where insider interception begins. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.9. This is the 111th session of the CISSP Exam Prep series. In this session, we'll meet the protocols that add security to specific channels. We'll answer several questions. What makes a protocol a secure communication protocol? What does the Internet Protocol Security Suite provide? How do the single sign-on and remote shell protocols protect access? What secures messaging and remote calls? And what does transport layer security do? Why does this matter beyond the exam? Because choosing the right secure protocol is a routine design decision. Imagine you are asked to protect a remote administration channel, a site-to-site link, or a messaging feature in an application. Each of these calls for a different protocol, and picking the wrong one leaves a gap. Knowing what each protocol was built to secure lets you match the tool to the channel with confidence. So what makes a protocol a secure communication protocol? It provides security services for a specific kind of communication channel. Rather than one universal shield, each of these protocols adds protection tailored to a particular job, whether that is a private tunnel, a login, a message, or a remote command. The common thread is that they layer confidentiality, integrity, or authentication onto communications that would otherwise travel exposed. Think of them as a set of specialized locks, each shaped for a different kind of door. What does the Internet Protocol Security Suite provide? A full bundle of protections built directly on the addressing layer. It uses public key cryptography to deliver encryption, integrity, replay protection, access control, and verification of where a message came from. Its main use is building private tunnels, and it can operate in two modes, one protecting just the payload and one protecting the whole packet. It is a bolt-on for the older address version, but native to the newer one. Picture an armored pipeline you can lay between two sites, sealing everything that passes through it. How do the single sign-on and remote shell protocols protect access? By guarding credentials and sessions. The single sign-on protocol lets a user authenticate once and reach many services, and it protects the logon credentials with strong, modern cryptography so passwords are not exposed on the network. The remote shell protocol is a strong example of end-to-end encryption. It wraps insecure legacy utilities in a protected channel, secures file transfers, and can even act as a host-to-host tunnel. Think of the first as one trusted badge that opens many doors, and the second as an armored tube around a conversation that used to travel in the open. What secures messaging and remote calls? Two more purpose-built protocols. The messaging protocol provides end-to-end encryption for voice, video, and text. And it is the cryptographic core inside a well-known secure messaging application. It ensures that only the two endpoints can read the exchange. The Secure Remote Procedure Call Protocol is an authentication service for communication between services across a network, guarding against unauthorized code being run on remote systems. One protects the conversation between people, the other protects the conversation between programs, and both insist on proving who is really on the line. What does transport layer security do? It is the workhorse encryption protocol that secures traffic at the transport layer by protecting the payload of reliable connections. You know it best as the encryption behind secure web browsing, but it can protect almost any application layer protocol. It supports secure client-server communication across an untrusted network, blocking, tampering, spoofing, and eavesdropping. And it offers one-way or, with certificates, two-way authentication. Because it can sit as the first payload of a connection, it can wrap everything above it. And importantly, it replaced the older, now retired secure sockets layer. Treat it as the general-purpose seal you reach for by default. So let's bring it together. Secure communication protocols are specialized locks, each shaped for a specific channel. The Internet Protocol Security Suite builds encrypted tunnels on the addressing layer, native to the newer address version. The single sign-on protocol protects credentials across many services, while the Remote Shell Protocol wraps logins, transfers, and tunnels in end-to-end encryption. The messaging protocol secures voice, video, and text. And the secure remote procedure call guards program-to-program calls. And transport layer security is the versatile default that replaced the older sockets layer. Match the protocol to the channel, and no conversation travels exposed. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.10. This is the 112th session of the CISSP exam prep series. In this session, we'll explore what happens when protocols stack inside one another. We'll answer several questions. How does layered encapsulation help? What is its dark side? What is a converged protocol? Which converged technologies should you know? What makes internet telephony both attractive and risky? And how does software-defined networking change the picture? Why does this matter beyond the exam? Because encapsulation is a double-edged design pattern you meet constantly. Imagine you allow web traffic out of your network but block file transfers, and an attacker smuggles the forbidden protocol inside the allowed one. Your filter never sees it. Understanding how layering both empowers and undermines your controls is what keeps you from trusting a boundary that has quietly been bypassed. So how does layered encapsulation help? By letting protocols nest inside protocols. A single message can be wrapped again and again, with web content inside the reliable transport protocol, inside the internet protocol, inside the local frame. You can add still more layers, such as slipping encryption in the middle to create secure traffic, or wrapping the whole thing in a tunnel to build a virtual private network. The benefits are real. A wide range of higher layer protocols can ride along, encryption can be inserted at multiple points, and the result is flexible and resilient. Think of nesting boxes, each one able to carry whatever you place inside it. What is the dark side of all this layering? The same flexibility undermines your controls. Because almost anything can be hidden inside, almost anything, encapsulation enables covert channels. If a network blocks one protocol but allows another, a tunneling tool can bury the forbidden protocol inside the permitted one and slip straight through the filter. This deception can even happen low in the stack, hiding a full session inside a protocol meant only for health checks. The drawbacks follow directly. Covert channels open up, filters get bypassed, and logical segment boundaries can be overstepped. A sealed box is convenient, but you cannot see what is inside it. What is a converged protocol? It is the merging of a specialty or proprietary protocol with a standard one, usually from the mainstream internet suite. The payoff is that you reuse your existing standard network infrastructure to carry special services, instead of deploying separate, dedicated hardware for each one. It lets one common network do many specialized jobs. Before we tour examples, hold on to that core idea. Convergence is about running the unusual over the ordinary. Picture a single set of highways carrying ordinary cars, delivery trucks, and emergency vehicles alike, rather than building a separate road for each. Which converged technologies should you know? Several ride storage and compute traffic over standard networks. A storage area network consolidates many storage devices into one network-accessible pool. And because it can be a single point of failure, you build in redundancy. A related internet storage standard offers a low-cost way to reach storage across local or wide area links. Another approach carries a high-performance interconnect inside ordinary network frames so it can run on existing infrastructure. And a modern high-speed link ties together processors, accelerators, and memory over one fast path for data-intensive work. The theme repeats. Specialized traffic, delivered over familiar plumbing. What makes internet telephony both attractive and risky? It is a converged protocol that packages voice and multimedia into network packets, and it is popular because it is cheap and flexible, often replacing traditional phone service. But riding on the network means inheriting the network's dangers. Caller identity can be forged for voice phishing, the phones and call managers can be attacked like any host, interception is possible when calls are not encrypted, and attackers can even hop across authenticated channels. Choose a solution that encrypts, since a secure real-time transport protocol exists precisely to blunt these threats. An open call is a conversation anyone nearby can record. How does software-defined networking change the picture? By separating the brains from the muscle. Traditional networks bake decisions into each router and switch, locking you into vendors and limiting flexibility. This approach splits the control layer, which decides where traffic should go, from the data layer, which simply forwards it. A central controller programs the whole network through interfaces, letting you mix and match cheaper hardware from any vendor and adjust settings from one console. A companion technique virtualizes network functions off dedicated appliances entirely, and the same thinking extends to virtual storage networks and to managing links between distant sites. Think of it as a control tower directing simple, interchangeable planes, rather than each aircraft flying on its own fixed instructions. So let's bring it together. Layered encapsulation lets protocols nest for flexibility, encryption, and tunneling, but that same power creates covert channels that bypass filters and cross boundaries. Converged protocols run specialized services over standard infrastructure, from storage networks to high-speed compute links. Internet telephony is a popular converged protocol that inherits network risks, so insist on encryption. And software-defined networking separates control from forwarding, centralizing management and freeing you from single-vendor hardware. See the layering clearly, and you can enjoy its benefits without trusting a boundary that has been quietly tunneled through. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.11. This is the 113th session of the CISSP exam prep series. In this session, we'll learn how and why networks get divided into smaller pieces. We'll answer several questions. Why segment a network at all? What are the physical forms of segmentation? What are the logical forms? How does a virtual private cloud fit in? And what is microsegmentation, right down to a single device? Why does this matter beyond the exam? Because segmentation is one of your most powerful tools for containing damage. Imagine an attacker who compromises a single workstation in your building. If your network is one flat space, they can roam freely to your servers. If it is well segmented, they hit a wall. Designing those internal boundaries and knowing which technique to use where is core architecture work you will do repeatedly. So why segment a network at all? Because dividing a network into smaller units pays off three ways. It boosts performance, since machines that talk often can sit together and broadcast traffic stays contained. It reduces communication problems, cutting congestion and containing disruptions like broadcast storms. And it improves security by isolating traffic and confining users to only the segments they are authorized to reach. Think of a large building divided into departments, each with its own door, so a problem in one wing does not spill into the rest. What are the physical forms of segmentation? They range from sharing a path to complete isolation. In-band segmentation runs both data and control traffic over the same infrastructure, so it often overlaps with logical division. Out-of-band segmentation splits management and control traffic onto a separate, dedicated network, keeping it away from production traffic that it might disturb or that might expose it. The strictest form is air-gap segmentation, a complete physical separation with no direct connection at all, and even wireless paths blocked. Picture 3 levels of privacy: a shared hallway, a separate service corridor, and a vault with no doors connecting it to anything. What are the logical forms of segmentation? Divisions created in software rather than in cabling. Virtual local area networks split one physical network into separate, isolated broadcast domains, grouping devices by department or function regardless of where they physically sit. Virtual private networks build encrypted channels across untrusted networks so remote users and sites connect safely. Virtual routing and forwarding lets one router hold multiple independent routing tables that never leak into each other. And virtual domains carve one device, like a firewall, into separate logical instances with their own policies. Think of drawing internal walls on a floor plan without moving a single physical partition. How does a virtual private cloud fit in? It is segmentation carried into the public cloud. A virtual private cloud is a virtualized network space that a cloud provider gives you, letting you create isolated, logically separated networks inside a shared public environment. You host your applications and resources in a dedicated, controlled area while still governing the network configuration yourself. Along with private internal networks, screened subnets, and extranets, it is simply another kind of segment. Picture renting a locked, private suite inside a large shared building with your own key and your own floor plan. What is microsegmentation? Right down to a single device. It is segmentation taken to its finest grain. Instead of dividing a network into a handful of zones, microsegmentation can isolate all the way down to a single high-value server or endpoint. Communication between these tiny zones is filtered, often requires authentication and encryption, and is closely monitored and logged. This makes it a cornerstone of zero trust, where nothing is trusted by default, and it is especially valuable for isolating sensitive workloads so an intruder cannot move sideways to reach them. It is supported by techniques like network overlays that stretch segments across distance, distributed firewalls and routers placed close to each workload, and detection systems watching every junction. Think of giving each critical room its own guard, its own lock, and its own camera, rather than trusting one perimeter fence. So let's bring it together. Segmentation divides a network to boost performance, reduce problems, and above all, improve security by containing intruders. Physical segmentation runs from shared in-band paths to separated out-of-band ones to fully air-gapped isolation. Logical segmentation draws boundaries in software through virtual local area networks, private networks, routing separation, and virtual domains. A virtual private cloud extends that isolation into the public cloud, and microsegmentation shrinks the zone down to a single device, enforcing filtering and authentication as a foundation of zero trust. Segment deliberately, and a breach in one place stays in one place. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.12. This is the 114th session of the CISSP Exam Prep series. In this session, we'll look at how modern networks push work outward. We'll answer a few questions. What is an edge network? And why move computing to the edge? How does data enter one of these networks? How does data leave? And how does separate edge networks talk to each other directly? Why does this matter beyond the exam? Because your users are impatient, and distance costs you milliseconds. Picture a streaming platform serving a live sports final to viewers on 3 continents. If every request travels back to one distant data center, the video stutters and the audience leaves. Understanding the edge lets you design for speed and resilience, and it lets you reason about where your data actually lives and who can touch it. What is an edge network, and why push computing outward? An edge network is a design that spreads processing out to devices near the people using them. Instead of forcing one central cluster to carry every workload, the outer devices shoulder a large share of it. The payoff is lower latency and better performance, because content and services sit closer to the user. Think of a coffee chain that bakes fresh pastries in each neighborhood shop rather than trucking them from one central kitchen across the city. The product reaches the customer faster and warmer. How does data actually enter an edge network? Through ingress points. These are the entry gates positioned at the outer boundary of the infrastructure, where outside data and content flow in. Placing them at the edge lets incoming requests arrive with as little delay as possible. Picture the front doors of that neighborhood shop, sited right on the busy street so customers walk straight in rather than hunting for a hidden side entrance. How does data leave the network again? Through egress points. These are the exits that steer traffic from your network out toward external destinations. Positioning them thoughtfully keeps the outbound flow smooth, so responses reach the user without a bottleneck. Think of a well-placed loading dock at the back of the shop, where finished orders roll out efficiently instead of clogging the same doorway customers use to come in. How do separate edge networks connect to each other directly? Through peering. Peering is when two edge networks build a direct link and swap traffic between themselves, skipping the middlemen in between. Cutting out those intermediaries trims latency and lifts overall efficiency, so data and services move between the networks faster. Imagine two neighboring shops that dig a private tunnel between their back rooms to share supplies, instead of routing every exchange through a distant central warehouse. So let's bring it together. An edge network pushes computing out to devices near the user to cut latency and lift performance. Data enters through ingress points sited at the boundary and leaves through carefully placed egress points. And peering links edge networks directly so they can trade traffic without intermediaries. Keep this outward-facing mindset, and you will design networks that stay fast and responsive no matter where your users sit. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.13, part 1. This is the 115th session of the CISSP exam prep series. In this session, we'll build the foundation of Wi-Fi security. We'll answer several questions. What makes a wireless network different from a cabled one? How does the 802.11 family evolve? How do clients and access points arrange themselves? What is the difference between a fat and a thin access point? How do you name and protect a wireless network? How do channels, surveys, and encryption protocols keep it fast and safe? Why does this matter beyond the exam? Because every wireless network you deploy is broadcasting into space where anyone can listen. Picture a busy hospital where doctors carry tablets from ward to ward, all riding the same Wi-Fi. Get the design and encryption right, and patient data stays sealed as staff roam the floors. Get it wrong, and someone in the parking lot can pull it out of the air. These fundamentals are what stand between convenience and exposure. What makes a wireless network different from a cabled one? It carries all the same threats as a wired network, plus a few of its own. Because the signal travels through open air, an attacker can eavesdrop from a distance without ever touching a cable. That same openness invites new forms of jamming and intrusion. This is why we call Wi-Fi an unbounded network, while a cabled network is a bounded one. Think of a wired network as a private letter in a sealed envelope, and wireless as a postcard anyone nearby can read as it passes. How does the 802.11 family keep evolving? 802.11 is the standard that governs wireless network communication. Over time, it has grown through a series of amendments, each typically pushing throughput higher and often adopting new frequency bands. The friendly Wi-Fi generation numbers you see on product boxes map back to these amendments. A helpful rule is that later amendments sharing a frequency with earlier ones usually keep backward compatibility. One caution for the exam: do not confuse this wireless family with the port-based authentication standard that has a very similar name but nothing to do with radio. How do clients and access points arrange themselves? In one of two modes. Ad hoc mode lets two wireless devices talk directly, with no central access point coordinating them, like two walkie-talkies chatting peer-to-peer. Infrastructure mode routes everyone through a wireless access point that enforces the rules of entry. Infrastructure mode comes in several flavors. A standalone setup links wireless clients only to each other. A wired extension bridges them onto the wired network. An enterprise extended design uses many access points, sharing one network name so users roam seamlessly. And a bridge deployment uses a wireless link to join two wired networks, handy between floors or buildings. What is the difference between a fat and a thin access point? It comes down to where the brains live. A fat access point is fully self-managed. It handles its own security, routing, and filtering locally, which makes it flexible for a home but tedious to configure one device at a time. A thin access point is little more than a radio. All the management is pulled into a central controller that oversees many of them at once. Picture a fat access point as a store manager who runs everything alone, and thin access points as cashiers, all directed from one head office. How do you name and protect a wireless network? Every network carries a service set identifier, the name clients look for. Related labels distinguish a single access point, a group of them covering a larger area, and the hardware address of a base station. Vendors ship default names that are widely known, so change yours to something unique before deployment. The name is announced in a beacon frame so devices can find it easily. You can silence that beacon, but do not mistake this for real security. An attacker with a sniffer still sees the name in ordinary traffic. Rely on strong encryption, not on hiding. How do you keep nearby access points from interfering? Through careful channel planning. Each frequency band is split into channels, like separate lanes on one highway. When two access points sit close together on overlapping channels, their signals collide and performance drops. The fix is to space physically close access points onto non-overlapping channels. In the lower band, a common trio of channels sits far enough apart to avoid clashing entirely. Higher bands were designed with wider gaps between channels, so neighbors interfere far less, and adjacent channels can even be bonded together for extra speed. How do you decide where to place your access points? You run a site survey. A site survey is a formal measurement of signal strength, quality, and interference, taken with a radio detector as you move a base station around the space. The goal is strong coverage where authorized people work, and weak signal leaking outside where intruders lurk. From those readings, you build a heat map, an overlay of signal strength on a floor plan. Hotspots reveal oversaturation, cold spots reveal dead zones, and both guide where to move antennas and how to tune power. Think of it as a weather map for your radio waves. How does a client first prove it belongs on the network? The original standard offered two authentication styles. Open system authentication asks for nothing real. As long as a radio can reach the access point, traffic flows, usually in the clear with no protection at all. Shared key authentication requires some proof before the network opens up. Over the years, shared key methods grew from an early, weak scheme into the far stronger protected access protocols we rely on now. Open access is like an unlocked lobby anyone can wander into, while shared key is a door that at least asks who you are. Why should you never trust wired equivalent privacy? Because it was broken almost immediately and has stayed broken. This earliest encryption option leans on a single static key shared across every access point and client, feeding a stream cipher that was implemented poorly. That combination gutted its strength. Today, the encryption can be cracked in under a minute with free tools. Treat it as a museum piece, not a defense. If you ever find it running, replacing it should be your first move. What was Wi-Fi protected access meant to fix? It was the bridge built to replace the broken scheme while a stronger standard was finished. Its big improvement was ditching the single static key. Instead, it negotiates a unique key set with each device and separates authentication from encryption. It was a real step forward for its time, but it too has since fallen to dedicated cracking tools and is no longer considered safe. You might still see it propping up ancient hardware, but that is a poor bargain you should retire whenever you can. Why is Wi-Fi protected access 2 the baseline you should demand? Because it replaced both earlier schemes with genuinely strong encryption. It swapped the old stream cipher for a modern block cipher mode built on the advanced encryption standard, which is held up against direct attack. That said, weaknesses have surfaced in its key exchange process, so keeping devices patched still matters. This version also introduced two authentication choices you must know. A pre-shared key, meaning a single fixed password for smaller settings, and an enterprise option that hands authentication off to a central identity service. Match the choice to the size and sensitivity of the deployment. So, let's bring it together. Wireless is an unbounded network exposed to eavesdropping and new attacks that cables never face. The 802.11 family evolves through amendments, and clients connect in ad hoc or infrastructure mode using fat or thin access points. Name your network deliberately, plan channels to avoid interference, and run site surveys to shape coverage. Above all, skip the broken early encryption, retire the temporary fix, and demand the modern protected access with proper authentication. In the next part, we push into even stronger protections and the attacks that target them. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.13, part 2. This is the 116th session of the CISSP exam prep series. This part picks up the wireless story where the last one paused, moving into stronger protections and other radio technologies. In this session, we'll widen the wireless picture. We'll answer several questions. What makes the newest protected access stronger? How does port-based authentication plug into Wi-Fi? Which extra protocols and features help or hurt security? How do you actually harden a deployment? And how do the other radio technologies around us work, from Bluetooth to the tiny tags in your badge? Why does this matter beyond the exam? Because Wi-Fi is only one radio your organization emits. Picture a retail store humming with staff tablets on Wi-Fi, wireless payment terminals, Bluetooth headsets, and access badges tapping doors all day. Every one of those signals is a possible way in. Knowing how each technology authenticates and where each one leaks is how you lock the whole radio environment, not just the obvious network. What makes the newest protected access stronger? It hardens the weakest link, the password exchange. The enterprise flavor steps up to a heavier encryption key, while the personal flavor keeps a strong modern cipher. The real leap is a new handshake that no longer sends your password across the air to prove it. Instead, it runs a zero-knowledge exchange, so both sides confirm they know the secret without ever transmitting it. It also shields management frames, giving those housekeeping messages confidentiality, integrity, and origin checks. Think of proving, a bank PIN by answering a challenge rather than shouting the number across the lobby. How does port-based authentication plug into Wi-Fi? Through a handoff standard that blocks a client from touching resources until it authenticates. Think of it as an authentication proxy sitting at the door. It does not check credentials itself. Instead, it hands the request off to your existing identity infrastructure, things like a central authentication server, certificates, smart cards, or tokens. Underneath sits a flexible framework that is not one authentication method, but a container for many. That container lets new authentication technologies drop into wireless and point-to-point links without reinventing the wheel. It is the plumbing that lets enterprise Wi-Fi lean on the identity systems you already run. Which extra authentication protocols should you know? Couple of wrappers around that flexible framework. One is a vendor-specific option built to patch an early weakness before the strong standard arrived. It was later shown to be crackable with a dedicated tool, so avoid it, and if you must use it, demand a long, complex password. A better choice wraps the authentication exchange inside an encrypted tunnel. Since the underlying framework was designed for already protected channels and often travels in the clear, tunneling it adds the confidentiality it lacks. Picture sending a sensitive form through a sealed courier pouch instead of an open interoffice envelope. Why is Wi-Fi protected setup a liability? Because convenience opened a hole. This feature was meant to make adding a new device painless, auto-connecting and authenticating the first client after you press a button or enter a short code. The trouble is that code, it splits into two halves that an attacker can guess one segment at a time, with the base station confirming each half. That design lets a brute force attack succeed in hours, dropping an intruder onto your network. It is on by default on most access points, so disabling it should be a standard step before deployment. If a device will not let you turn it off, update the firmware or replace the unit. Can filtering by hardware address keep intruders out? Not reliably. A hardware address filter is a list of approved device identifiers, and the access point blocks anything not on it. It sounds tidy, but it only fits small, static environments. and even there it leaks. The frame header that carries those addresses stays readable even under strong encryption, so an attacker can sniff an approved address and spoof it. On top of that, many modern phones rotate their address at random, so treat this as a mild speed bump, never as a real gate. How much does antenna choice and placement matter? More than people expect. The common straight antenna radiates in every direction, which suits a base station sitting in the middle of a space. Directional types instead focus their energy one way, useful for reaching a distant point or a specific zone. For good coverage, center your equipment. Avoid solid obstructions, steer clear of reflective metal surfaces, and keep away from electrical noise. If signal is still poor after a survey, nudge the power level in small steps and note the original setting, since sometimes lowering power actually improves things. Think of aiming a flashlight versus lighting a whole room. What does a captive portal add? A gatekeeping web page. When a new client connects, the portal redirects it to a page before letting any traffic through. That page might demand a login, an access code, or payment, and it often forces the user to accept an acceptable use policy first. You have met these at hotels, airports, and cafes, but they work on wired connections too. The point is simple. Anywhere an owner wants to limit access to paying, agreeing, or known users, this page becomes the checkpoint. Think of a coat check you must clear before entering the venue. So what does a solid Wi-Fi deployment look like in order? It stacks several habits together. Start by updating firmware and replacing the default administrator password with something long and unique. Turn on modern, protected access encryption and pick an authentication mode that fits your scale. Change the network name off the vendor default and treat the wireless side as untrusted, separating it from the wired network with a firewall. Layer on wireless intrusion detection and prevention. Consider requiring a VPN across the link, add a captive portal, and log every wireless event. No single step is magic. The strength is in the stack. How do wireless signals actually share the limited airwaves? Through spectrum techniques that let many transmissions coexist. Radio communication rides waves measured by frequency, and there is only so much usable spectrum to go around. Spread spectrum splits a message across several frequencies at once, sending pieces in parallel. Some methods hop across frequencies, one at a time. Others transmit on many simultaneously with special coding to survive interference, and still others pack signals tightly so they do not clash. Others let multiple users share one band by slicing it into time slots or by tagging each user with a unique code. Picture a crowded room where people avoid talking over each other by taking turns, whispering on different pitches, or each speaking a private language. What should you know about Bluetooth and its relatives? That it is convenient and usually unencrypted. Bluetooth links paired devices over short distances on a common band. And by default, most implementations send data in the clear, often relying on trivial pairing codes. A low-energy variant sips power for wearables, sensors, and medical gear while keeping similar range. And a related low-power standard for smart devices does encrypt its traffic. Convenience aside, Bluetooth invites a family of attacks. Attackers can capture its packets, flood a device offline, push unwanted messages, quietly steal data, or even seize remote control and turn on a microphone. The best defense is blunt. Minimize its use, especially in public, and switch it off when you are not actively using it. How do the tiny tags in badges and phones work? Through two related, short-range technologies. The first can be powered from a distance by a reader's magnetic field, letting it transmit a stored code without a battery, which makes it great for inventory, but also a privacy concern, since anyone with a reader could note your tag as you pass. The second is a close cousin that only works within a few centimeters, so you tap or touch devices together to trigger it. That tight range is a feature, powering contactless payments and quick device pairing while limiting who can reach it. But even it faces eavesdropping, tampering, and replay, so leave it disabled until you actually need it. So let's bring it together. The newest protected access strengthens the handshake and shields management frames, and port-based authentication hands Wi-Fi off to your existing identity systems through a flexible framework. Know the tunneling protocol that adds encryption, and disable the setup feature and hardware address filtering that offer false comfort. Plan antennas, use captive portals, and follow the layered deployment checklist. Beyond Wi-Fi, understand how spectrum is shared, why Bluetooth needs restraint, and how short-range tags trade range for both convenience and exposure. In the final part, we turn to the attacks that target wireless directly. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.13, part 3. This is the 117th session of the CISSP exam prep series. In this closing part, we turn from building wireless networks to the attacks that target them. In this session, we'll walk the wireless attacker's toolkit. We'll answer several questions. How does an attacker find your networks? What is a rogue access point? And how is an evil twin sneakier? How do management frames get weaponized? And what do jamming, weak randomness, and replayed traffic have in common? Why does this matter beyond the exam? Because even a well-built wireless network stays a target. Picture a co-working space full of freelancers who trust whatever network their laptops remember. An attacker in the corner can quietly impersonate a familiar network and harvest sessions all afternoon. When you know how each of these attacks works, you can spot the warning signs, coach your users, and place the right detection so the corner attacker never gets that afternoon. How does an attacker find your networks in the first place? By scanning for them. War driving is the practice of roaming an area with a detection tool, hunting for wireless signals the attacker has no right to use. The tool might be a phone, a laptop with a wireless card, or even a drone flying overhead. Any active network that is not sealed inside a shielded enclosure gives itself away, because the base station is always radiating. A scanner reveals the network name, its channel and frequency, and what encryption, if any, is in use. Think of a burglar strolling a neighborhood, quietly noting which houses have alarms and which leave the windows open. What is a rogue access point? An unauthorized access point riding on your network. It might be planted by an employee chasing convenience, slipped in by an intruder who got inside, or run by an attacker from outside. However it arrives, it usually skips proper security, punching an unregulated hole into your otherwise guarded network. One variant clones a legitimate network name and hardware address at higher power to lure your existing clients away from the real access point. Another simply advertises an inviting name to attract fresh visitors. Your defense is to run wireless intrusion detection and hunt these down, often triangulating the source with a scanner and a directional antenna. Picture a fake toll booth set up on a road to collect from unwitting drivers. How is an evil twin sneakier than an ordinary rogue? Because it lets the victim's own device pick the trap. Every time your device joins a network, it remembers that profile and later broadcasts requests to reconnect, naming the networks it trusts. An evil twin listens for those requests, then instantly impersonates whichever network your device is calling for, offering a plaintext connection. Your device accepts because the client trusts the base station to set the terms of security. Once connected, the attacker sits in the middle, poised to hijack sessions and steal credentials. Your defenses are to watch which network you actually join, prune old saved profiles, and lean on a VPN whenever you go wireless. Think of an imposter who answers to whatever name you call out, then walks you the wrong way. How do management frames get turned into weapons? By abusing the messages that manage connections. A disassociation frame normally tells a client to drop one access point as it moves to another in the same coverage area. Sent maliciously, it simply knocks a client off the network. A related deauthentication frame does much the same, forcing an immediate disconnect. Attackers spoof these to expose a hidden network name, to deny service by repeatedly kicking a client off, to hijack a session while the real client is locked out, or to shove a client toward a fake access point. Your best defenses are the newest protected access and a wireless intrusion detection system watching for the abuse. Picture someone yanking your phone call dead the instant it connects, over and over. What is jamming, and how do you respond? It is deliberate radio noise meant to drown out communication. By flooding the airwaves and wrecking the ratio of signal to noise, jamming interferes with or fully blocks a network. Your first moves are practical. Reposition devices, check whether something is simply sharing your frequency or channel, and change the channel on gear you control. If it is a genuine attack, Try to triangulate the source, and if it originates outside your walls, bring in law enforcement. Think of someone blasting an air horn in a quiet meeting so no one can be heard. Why is a weak random number a security hole? Because cryptography leans on unpredictability. Modern encryption mixes in a random value to keep patterns from repeating and to resist prediction. That value becomes a weakness when it is too short, reused, sent in the clear, or chosen poorly. Attackers who collect enough predictable values can chip away at the encryption, which is exactly how the earliest wireless encryption was broken. The lesson generalizes. When randomness is thin, the math protecting your data gets thin with it. Picture a combination lock that only ever spins through a handful of numbers, so a patient thief eventually walks right through. What makes a replay attack effective? It reuses captured traffic to fool a system. The attacker records legitimate communication, often an authentication exchange, then retransmits it later to open a session as if they were the real party, all without ever learning the actual credentials. In the wireless world, this can spoof new connection requests or simply flood a base station with repeated requests to starve it of service. Your defenses build in time and freshness. Keep firmware current, run intrusion detection, and use one-time mechanisms, timestamps with expirations, challenge and response exchanges, and sequence session identifiers. Think of a door that accepts a recorded password today, so anyone who taped it yesterday strolls in. So let's bring it together. Attackers first map your networks by scanning and war driving, then set traps with rogue access points and stealthier evil twins that your own devices choose. Management frames get weaponized for denial of service, hijacking, and misdirection. Jamming drowns your signal, weak randomness cracks your crypto, and replayed traffic slips past authentication. The through line is that visibility and freshness are your friends. Run wireless intrusion detection, prune trust, demand strong encryption, and build time into your authentication. That closes out the wireless story. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.14. This is the 118th session of the CISSP exam prep series. In this session, we'll look up at satellite communications. We'll answer a few questions. What are satellite communications, and what do they carry? What are the three main orbits a satellite can sit in? And how do those orbits trade off signal strength, coverage, and delay? Why does this matter beyond the exam? Because more of your traffic than ever may ride a link to space. Picture a remote research station on a frozen coastline with no cables for hundreds of miles, keeping its team online entirely through the sky. When you understand how orbits shape signal, latency, and coverage, you can judge whether a satellite link fits a use case, and where its delay or exposure might undercut a design. What are satellite communications, and what do they carry? At heart, they are radio waves bouncing between spots on the ground and a spacecraft circling above. That simple relay carries an enormous range of traffic, including telephone calls, television, radio, internet access, and military communication. The satellite acts as a mirror in the sky, catching a signal from one location and reflecting it onward to another far away. Think of a lighthouse keeper on a hill relaying messages between two valleys that cannot see each other directly. What are the three main orbits a satellite can occupy? Satellites sit in one of three altitude bands, and the band shapes everything about the link. There is a low band closest to the surface, a middle band far higher, and a high band far out where the satellite keeps pace with the planet. As you climb higher, the footprint each satellite can cover grows, but the signal weakens and the delay increases. Keep that trade-off in mind as your map for all three. Picture three cameras filming a stadium, one on the field, one in the upper deck, and one in a blimp, each seeing more of the crowd but from farther away. What defines a low-orbit satellite? It flies closest to the ground, which gives it a strong signal but a restless position. Because it does not stay fixed over any one spot, you need many of them working together to hold steady coverage. This is exactly why space-based internet services launch huge constellations of thousands of satellites, so that as one slips out of view, another slides in behind it. Think of a relay team where runners keep handing off the baton so the race never stops, even though no single runner covers the whole track. What changes with a medium orbit satellite? It sits higher, so it lingers over a location longer than a low orbit satellite and covers a wider footprint from a single spacecraft. The cost of that height is a weaker signal and more delay, since the waves travel farther. It is a middle ground, trading some responsiveness for broader, steadier reach. Picture watching a parade from a second-floor balcony instead of the curb. You see more of the street at once, but the marchers look smaller and their voices arrive a beat later. What makes a high, geostationary orbit special? A satellite this far out circles the planet at exactly the speed the planet turns, so it appears to hang motionless above one fixed point. That stillness is its superpower. Ground stations do not have to track it across the sky and can simply aim a fixed dish and leave it. Its footprint is the largest of all, though its great distance brings the highest delay. Think of a hot air balloon tethered permanently over a fairground, always in the same spot, so every stall can just point a sign straight up at it. So let's bring it together. Satellite communications relay, radio waves between the ground and spacecraft, carrying everything from phone calls to internet to military traffic. They occupy 3 orbits, and altitude drives the trade-offs. The low band gives strong signals but needs many satellites for coverage. The middle band widens the footprint at the cost of signal and delay. And the high, geostationary band hangs fixed in place with the broadest reach but the greatest latency, match the orbit to what the link actually needs. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.15. This is the 119th session of the CISSP Exam Prep series. In this session, we'll unpack the cellular networks in everyone's pocket. We'll answer several questions. How is a cellular network actually organized? How far does its encryption really reach? What separates the recent generations of service? And what security risks come with treating a phone as a doorway into your network? Why does this matter beyond the exam? Because your workforce carries the office in a jacket pocket. Picture a sales team closing deals from airports and hotel lobbies, tethering laptops to their phones to reach internal systems. Every one of those connections rides a carrier's network you do not control and cannot fully trust. Knowing where cellular protects data and where it quietly stops protecting it is how you keep that convenience from becoming a leak. How is a cellular network actually organized? Around areas of coverage called cells. Each cell centers on a primary transceiver, the tower or base station that mobile devices talk to. As a phone moves, it hands off from one cell to the next, so coverage feels continuous. The service itself is labeled by generation, the familiar shorthand you see climb from one number to the next as the technology advances. Think of a chain of neighboring watchtowers, each covering its own patch of countryside and passing a traveler along as they walk from one patch into the next. How far does cellular encryption really reach? Not as far as most people assume. Your traffic is generally encrypted only on the hop from your device to the nearest tower. Once it lands and travels onward over the carrier's wires, it can effectively be in the clear. That means cellular is not a safe place for anything truly sensitive on its own. The fix is to protect the data yourself before it ever leaves the phone, using an encrypted application or a VPN so the content stays sealed end to end. Picture an armoured car that guards your package only to the edge of town, then drops it onto an open truck for the rest of the journey. What defines the 4th generation of cellular service? It is the widely supported baseline most devices still use. It lets phones reach respectable mobile speeds, with stationary equipment going faster still. Its big shift was moving to Internet Protocol-based communication for both voice and data, leaving behind the old circuit switch telephone approach. It is delivered through a few transmission systems, the most common being the one you see branded on your phone's status bar. Think of it as the reliable, well-paved main highway that nearly every vehicle already knows how to drive. What changes with the 5th generation? It reaches for much higher speed. By using higher radio frequencies than earlier generations, it delivers dramatically faster transmission, though those higher frequencies do not travel as far. You will increasingly find it embedded not just in phones and tablets, but in industrial control systems and connected devices. That spread is exactly why it matters to you. As this generation shows up in more corners of the business, your team needs to know where it is available and enforce security requirements on those communications. Picture a new express lane that is blazingly fast, but only covers shorter stretches, so you plan around its reach. What security risks come with cell phones as doorways? Several, and they stack. First, traffic across a carrier's network, whether voice, text, or data, is not guaranteed to be secure. Second, with the right sniffing equipment, your transmissions can be intercepted, and an attacker can even stand up a fake tower to run an adversary in the middle attack. Third, and most dangerous for you, using a phone's connection to reach the internet or the office turns that device into a potential bridge, quietly opening an insecure path into the company network. The defense is to treat these devices as untrusted entry points and wrap their sensitive traffic in your own encryption. Think of a side gate someone props open for convenience. Unaware it lets strangers walk straight into the yard. So let's bring it together. A cellular network is organized into cells served by towers, with service labeled by generation. Its encryption covers only the hop to the tower, so protect sensitive data yourself. The fourth generation is the Internet Protocol-based baseline nearly everyone runs, while the fifth trades reach for far greater speed and spreads into industrial gear. And every cellular device is a potential bridge into your network, vulnerable to interception and fake towers. Treat these connections as untrusted, and layer your own encryption on top. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.16. This is the 120th session of the CISSP Exam Prep series. In this session, we'll explore how content reaches users quickly at scale. We'll answer a few questions. What is a content distribution network, and how does it stay fast? Can this idea work without a fleet of company servers? And what closely related platform delivers services the same way? Why does this matter beyond the exam? Because performance and availability are security concerns, not just marketing ones. Picture a breaking news site slammed by millions of readers the moment a major story drops. If every request funnels to one origin server, it buckles, and an outage looks a lot like a denial of service. Understanding how content is distributed helps you design for availability under load and reason about where your data is cached and who runs those far-flung nodes. What is a content distribution network, and how does it stay fast? It is a spread-out collection of servers placed in many data centers across the internet, all working to keep hosted content quick, reliable, and highly available. Instead of parking media in one central spot and shipping it everywhere, the content is copied to many geographically scattered staging points close to clusters of users. That layout naturally balances the load, so no single server strains under every request, and each user is served from somewhere nearby. Think of a popular book stocked in libraries in every town, so no reader has to travel to one distant central archive and no single branch gets mobbed. Can this idea work without a company running the servers? Yes, through a client-based approach. Rather than relying on the provider's fleet of distributed servers, this model turns the users themselves into distribution points, each sharing pieces of content with others. It is commonly known as a peer-to-peer arrangement, and the most widely recognized example is a well-known file-sharing protocol. The effect is similar, spreading the delivery burden across many locations, but the heavy lifting comes from the participants rather than a central operator. Picture neighbors lending each other chapters of the same book, so the load never lands on one library at all. What closely related platform delivers services the same way? A service delivery platform. It is a collection of components that together form the architecture for delivering a service, and it shows up in areas like internet voice, streaming television, software delivered online, and online gaming. It is a close cousin of the content network, since both exist to support and efficiently deliver a resource, whether that resource is a service or media. Its goal is to provide seamless communication services to other content or service providers. And like content networks, it can be built from small, independent building blocks. Think of a shared kitchen that lets many food stalls plate and serve their dishes through one smooth, common counter. So let's bring it together. A content distribution network scatters copies of content across many servers near users, balancing loads so delivery stays fast, reliable, and available. The same idea can run without a central fleet through a peer-to-peer model where users share the load themselves. And a service delivery platform applies the same efficient delivery thinking to services rather than media. Across all three, the theme is the same. Bring the resource closer to the user and spread the burden so no single server buckles under demand. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.17, part 1. This is the 121st session of the CISSP exam prep series. In this session, we'll map the building blocks of a secure network. We'll answer several questions. How do private network zones differ from one another? What sits in the buffer between the public and the private? Which way does traffic actually flow? How do you keep hardware reliable? What do the core devices do? And how do collision and broadcast domains fit? And how does network access control keep unwanted machines out? Why does this matter beyond the exam? Because you cannot secure what you cannot picture. Imagine inheriting a sprawling campus network with no diagram, just a room full of blinking boxes, until you know which zone is trusted, which device splits traffic, and where outsiders are allowed in. Every control you add is a guess. Getting fluent in these components lets you design deliberately, avoid single points of failure, and place your defenses where they actually count. How do private network zones differ from one another? Chiefly by who is allowed in. An intranet is a fully private network that hosts internal services like web pages, email, and file access for your own people only. An extranet is a carved-out section that behaves like an intranet internally, but also serves specific outsiders. Think chosen partners, suppliers, or a remote sales force. The dividing line is the audience. One is strictly internal, the other deliberately opens a controlled slice to trusted external parties. Picture an office building where most floors are staff only, but one conference floor is set aside for visiting business partners. What sits in the buffer between the public and the private? A screened subnet. It is a special purpose zone built for low trust and unknown users, like the public reaching a web server without letting them touch your internal network. You can build it with two firewalls, one facing the internet and one facing the intranet, so the subnet sits sandwiched and screened between them. Or you can use a single multi-home firewall with three interfaces, one to the internet, one to the subnet, and one to the intranet. Either way, it is a controlled reception area. Think of a hotel lobby where anyone may enter, but a second set of locked doors guards the guest floors beyond. How does a screened host differ from that subnet? It is a single, hardened system placed just inside a network segment, acting as a gatekeeper. All inbound traffic routes to it first, and it serves as a proxy for the trusted systems behind it, filtering what comes in and hiding the identity of the internal machines. Where the screened subnet is a whole zone, the screened host is one choke point doing the guarding. Picture a single reception desk that every visitor must clear before anyone in the building will take their message. Which way does traffic actually flow inside your network? In two directions worth naming. East-west traffic is the flow that stays within a network, data center, or cloud environment, moving between internal systems side to side. North-south traffic is the flow crossing the boundary, coming in from or going out to external systems. Knowing which is which shapes where you inspect and segment. Picture a warehouse where forklifts shuttle goods between aisles all day, that is east-west, while the loading docks handling trucks arriving and leaving are north-south. How do you keep the physical hardware reliable? By planning for power, warranty, and support. Reliable power is foundational. So beyond surge protection and battery backup, consider redundant power supplies. A common design has two supplies, each carrying half the load. So if one fails, the other instantly shoulders the full demand. and some even allow hot swapping without downtime. Beyond power, always ask about warranty and return terms when you buy, so a failed device can be refunded or replaced. And confirm what technical support is available, since advanced gear may demand vendor expertise you do not have in-house. Think of buying a delivery van. You check not just the engine, but the spare tyre and the service plan. What do the core network devices do, and how are they layered? They map neatly onto the lower layers of the reference model. At the lowest layer sit signal boosters, repeaters, concentrators, and amplifiers, plus the hub, which is really just a multi-port repeater. One layer up work bridges and switches, which move frames by hardware address, with switches able to carve out separate segments. At the next layer up sit routers, steering traffic by logical address between networks. A helpful anchor is that the lower the device, the dumber and more broadcast prone it is, while higher devices make smarter, more targeted decisions. Picture a mail system where a simple loudspeaker shouts to everyone, a sorting clerk hands mail to the right desk, and a regional dispatcher routes between whole buildings. Why do collision and broadcast domains matter here? Because the device you choose decides how chatter spreads. A collision happens when two systems transmit at once on a shared path, and the collision domain is the group of systems that could clash that way. Any device at the second layer or higher splits a collision domain. A broadcast is one system reaching all others, and the broadcast domain is everyone who hears that shout. It takes a third layer device to divide a broadcast domain. So the smarter the device, the more it contains the noise. Picture a crowded room. A low partition stops people from bumping into each other, but only a solid wall stops a shout from carrying across. What other specialized nodes round out a network? A handful of purpose-built helpers. A jump server is a hardened waypoint you connect through to reach a sensitive system more safely, common in screen subnets and cloud networks, and it should only ever accept encrypted connections. A sensor gathers information and ships it back to a central system for analysis. A collector is any system that quietly records specific activity into a log, and an aggregator pulls many inputs together into one stream for processing. Many of these run on a system on a chip, a tiny integrated computer that packs a processor, memory, and networking onto a single chip, powerful but often too minimal for rich security features. Picture a security office where guards feed observations to one desk that logs, combines, and forwards them upward. How does network access control keep unwanted machines out? By enforcing your security policy automatically at the point of connection. Its job is to check that every device joining the network is patched, compliant, and authorized, and to keep the rest out. It can act before admission, demanding a device meet requirements before it may communicate, or after admission, judging access by ongoing user activity. It can run through an agent installed on each system, or agentlessly by scanning from a central server. Non-compliant machines can be quarantined to a remediation area until they are fixed. Think of a doorman who not only checks your invitation but also confirms your vaccination card before letting you into the party. So let's bring it together. Intranets serve your own people. Extranets open a controlled slice to trusted outsiders. And a screened subnet buffers the public from the private, while a screened host does the same job as a single choke point. Traffic flows east-west, inside, and north-south across the boundary. Keep hardware reliable with redundant power, warranties, and support. Know your devices by layer, from dumb repeaters and hubs up to smart routers. And remember which devices split collision versus broadcast domains. Add specialized nodes like jump servers and sensors, and let network access control gate every machine at the door. In the next part, we dig into firewalls and proxies. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.17, part 2. This is the 122nd session of the CISSP exam prep series. This part focuses on the workhorses of network filtering, firewalls, and proxies. In this session, we'll master how firewalls and proxies filter traffic. We'll answer several questions. What is a firewall really doing? And by what default? How do you filter at the edge? What can a firewall not do on its own? What are the major firewall types, and how do proxies and content filters extend the picture? Why does this matter beyond the exam? Because the firewall is where most people concentrate their trust, and that trust is easy to misplace. Picture a new online store where a single firewall rule, written a little too loosely, quietly exposes an internal admin panel to the entire internet. Firewall failure is usually human error, not a broken box. When you truly understand what each type does and does not see, you write tighter rules and stop treating one appliance as the whole defense. What is a firewall really doing, and by what default? It is filtering traffic between zones of different trust, using a defined set of rules. Those rules, sometimes called access control lists, sort authorized traffic from unauthorized or malicious traffic, and only the approved traffic crosses. The critical mindset is denied by default. Nothing passes unless an explicit rule allows it, and a final catch-all denies everything else. Rules are often evaluated in priority order until the first match wins, so ordering matters. Think of a strict guest list at a private event. If your name is not on it, you simply do not get in, no matter how you ask. How do you filter traffic right at the edge? By blocking obviously bogus packets before they get deep. A hardened, exposed system meant to absorb attacks is called a bastion host, named for the fortified guardhouse that once stood in front of a castle gate to take the first blows. At the boundary, ingress and egress filters catch spoofed traffic. For instance, an inbound packet claiming to already be from inside, or an outbound packet pretending to come from outside. You can also drop traffic to or from known bad addresses far upstream before it ever reaches you. Picture a checkpoint on the road well outside the city, turning away suspicious vehicles long before they reach downtown. What can a firewall not do on its own? More than you might hope. A firewall generally cannot stop malware riding inside otherwise allowed traffic, cannot prevent a careless insider from leaking data, cannot catch an attacker already behind it, and cannot protect data once it has crossed. It is also a natural single point of failure, since so much protection concentrates in one spot. The answer is to add capabilities, either through companion tools or through an all-in-one appliance that bundles many functions together. These consolidated boxes go by names like multifunction device, unified threat management, and next-generation firewall. Think of a front door lock, essential but useless against a leak in the roof or a thief already inside. What are the major types of firewalls? There are several, and real deployments often blend them. The simplest just inspects packet headers one at a time. The next understands a specific application or service. Another concerns itself only with setting up sessions between trusted partners. A more capable type tracks the full state and context of a conversation, and the most feature-rich bundles many of these together. A useful way to remember them is by how much context each one considers. From a single isolated packet all the way up to an entire ongoing conversation and its payload. Picture inspectors ranging from one who glances at each envelope to one who follows the whole correspondence to understand it. What does a static packet filtering firewall do? It makes the most basic decision possible. It examines a message header, usually the source and destination addresses and the port numbers, and allows or denies based on that alone. Crucially, it is stateless, judging each packet entirely on its own with no memory of what came before. That makes it fast and simple but blind to context. Think of a bouncer who only checks the address on each envelope and never notices that 100 of them just arrived from the same suspicious sender in a row. What sets an application-level firewall apart? It understands the actual service it is protecting. Operating at the top layer of the model, it filters based on a specific protocol or application, which lets it make far smarter decisions about what is really being requested. A common example guards websites by enforcing strict rules on traffic to and from a web application, blocking web-specific attacks. A cloud-delivered variant extends this idea as a subscription service, filtering between cloud resources and on-premises systems, while layering on extras like inspection of encrypted traffic and data loss prevention. Picture a specialist reviewer who actually reads the contents of a form to judge whether the request makes sense, not just the envelope. What is a circuit-level firewall focused on? The connection itself, not its contents. It works to establish communication sessions between trusted partners, caring about whether a session should be set up rather than what flows through it once it is. It leans on simple rules about addresses and ports, and it too is stateless. A related lightweight tool restricts access to ports and resources based on user or system identity, a basic form of port-based access control. Think of a switchboard operator who decides whether to connect your call based on who is calling whom without ever listening in on the conversation. Why is stateful inspection more powerful? Because it remembers the conversation. Instead of judging packets in isolation, it tracks the state, session, and context of traffic, noting how the current packet relates to earlier ones in the same exchange. That lets it safely allow the expected reply to a valid outbound request by creating a temporary rule that lasts only as long as the conversation. It can spot malicious patterns invisible to single packet checks, and it may even perform deep inspection of a packet's actual payload, not just its header. Picture a guard who recognizes that a returning delivery truck matches the one they waved out an hour ago and lets it back in without fuss. Where do host-based and internal segmentation firewalls fit? They protect from the inside. A host-based firewall installs directly on an individual client or server, defending that one machine from both risky local activity and network-borne threats, and it can range from simple filtering up to the most advanced type. An internal segmentation firewall instead sits between internal segments or divisions, stopping malicious code or harmful traffic from spreading laterally once something is already inside. It is a common building block of fine-grained segmentation. Picture interior fire doors in a building. They will not stop a fire from starting, but they keep it from racing through the whole structure. How do proxy servers extend all this? By standing in the middle between clients and servers. A proxy accepts a client's request, rewrites the source so the client stays hidden, forwards it out, and relays the reply back to the right requester. A forward proxy handles internal users reaching outside services, while a reverse proxy handles outside requests coming into internal services, often sitting at the edge of a screened subnet. If clients are pointed at the proxy without being configured for it, it is transparent, and if clients are explicitly set to use it, it is non-transparent. Along the way, proxies can also cache content and filter sites. Think of a personal assistant who places all your calls under their own name, so the people you contact never see your direct line. What do content and URL filters add? Targeted control over what users can reach. Content filtering inspects the payload of traffic, often matching against a blocked list of unwanted terms or addresses to decide what is allowed through. URL filtering, also called web filtering, blocks access based on all or part of a web address, whether a whole domain, a path, or a file type, and it can pull updated block lists from vendors. A combined web security gateway rolls content and URL filtering together with malware scanning, and sometimes messaging and email filtering too. Picture a librarian who not only bars certain titles, but also reads inside the books to catch banned passages. So let's bring it together. A firewall filters between trust zones on a deny by default stance, with ordered rules and a final catch-all deny. Harden the edge with a bastion host and ingress and egress filters, and remember what a firewall cannot do alone, which is why multifunction appliances exist. The types climb in context, from stateless header checks to application-aware and circuit-level filters, up to stateful inspection with deep packet analysis, plus host-based and internal segmentation firewalls. Proxies mediate and hide clients, and content and URL filters govern what users may reach. In the next part, we turn to endpoint security. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.17, part 3. This is the 123rd session of the CISSP Exam Prep series. This part shifts from the network core to the devices at its edges. Endpoint security. In this session, we'll secure the endpoints, not just the network. We'll answer several questions. What does endpoint security actually mean? Why did distributed computing make this harder? What new vulnerabilities does it introduce? And how do you safeguard against them? And how have detection and response tools evolved to keep up? Why does this matter beyond the exam? Because attackers rarely bother with your hardened core when a laptop is easier. Picture a consulting firm where every analyst carries a laptop full of client data through cafes and trains. One unpatched machine or one stolen device can undo every dollar spent on the perimeter. Endpoint security is where the theory of defense in depth meets the messy reality of real people and real devices. What does endpoint security actually mean? It means each device is responsible for its own protection, regardless of whatever security the network provides. Sometimes this is phrased as the end device defending itself. But the sharper truth is that any weak point anywhere, on the border, on a server, or on a single client, puts the entire organization at risk. So endpoint security is not about trusting the network to cover you. It is about hardening every last device as if it stood alone. Think of a ship with watertight compartments. One flooded cabin should never be allowed to sink the whole vessel. Why did distributed computing make security harder? Because it scattered the things worth protecting. Computing moved from a central model, where everything lived on one guarded system, to a client-server model, where independent desktops both do their own work and reach out to network servers. Now processing and storage sit spread across many clients and many servers, and even the links between them may stretch beyond the local site. Security can no longer camp at one central host. It has to be addressed everywhere at once, on every machine and across every connection. Picture a company that moved all its cash from one guarded vault into 1,000 small tills, each of which now needs its own lock. What new vulnerabilities does a distributed environment introduce? Ones that a single central system never faced. Desktops and laptops hold sensitive data, yet are operated by users who may lack security awareness, so the architecture has to compensate. Those same machines are doorways to critical systems, and if misused or compromised, they become threats themselves. Communication gear like modems and wireless adapters can open unwanted paths inside. Downloads invite malicious code. Portable devices can be physically stolen, and data living only on a client is often never backed up. Each of these is a crack a distributed design opens that a monolithic one simply did not. Picture a mansion with 100 windows instead of a single fortified door. How do you safeguard all those endpoints? By layering policies and controls over every client, screen, email, and downloads so they cannot smuggle in malware. Enforce strong access controls, including multi-factor authentication and encrypt files, especially full drive encryption on anything portable. Lock screens after a timeout, separate high-privilege processes from ordinary ones, and segment the network so one compromised client cannot topple the rest. Label sensitive materials, back up client data centrally, train users continually, and fold desktops into disaster recovery and continuity planning. To apply all this consistently, image a properly configured device and roll that baseline out everywhere. Think of issuing every employee the same locked, standardized toolkit rather than letting each rig their own. What is endpoint detection and response? It is the evolution of traditional antivirus, intrusion detection, and firewalls into one smarter guard on the device. It works to detect, record, evaluate, and respond to suspicious activity, whether that activity comes from bad software or from users behaving badly. It is really continuous monitoring focused on both the endpoint itself and the traffic reaching it. Some versions analyze on the device, others report to a central or cloud engine. The goal is to catch advanced abuses that ordinary antivirus misses, cut false positives, and respond faster to incidents. Picture a vigilant security camera that not only records but recognizes trouble and sounds the alarm on its own. How does this expand into the broader detection family? Through several related acronyms worth distinguishing. Managed detection and response is a service that watches your whole environment in real time, not just endpoints, blending technologies like log management, traffic analysis, and endpoint tools. An endpoint protection platform is the more proactive cousin of endpoint detection, adding a predict and prevent emphasis rather than just detect and respond. An extended detection and response is not a single tool but an integration of these ideas into one solution, reaching beyond endpoints to network analysis and intrusion functions too. Think of upgrading from one camera to a staffed monitoring service to a full command center watching every feed at once. Who runs all this when you cannot? A managed security service provider. Such a provider can deliver these advanced detection and response solutions under central management, deployed on your premises, in the cloud, or as a hybrid. Their operations are often overseen from a security operations center, which may itself be local or remote. The payoff is that you gain access to sophisticated tools and, just as importantly, to seasoned security professionals you would struggle to hire and keep in-house. Picture hiring a professional security firm to staff and run your control room around the clock, rather than training your own night watch from scratch. So let's bring it together. Endpoint security holds each device responsible for itself because one weak machine endangers everyone. Distributed computing, scattered data and processing across countless clients and servers, opening vulnerabilities a central system never had. You counter them by layering policies, encryption, access controls, segmentation, backups, training, and consistent imaging. Detection has evolved from plain antivirus into endpoint detection and response, then into a wider family of managed, preventive, and extended solutions, which a managed provider can run for you. Secure the edges as carefully as the core. In the next part, we turn to cabling, topologies, and transmission media. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 11.17, part 4. This is the 124th session of the CISSP exam prep series. This part gets physical, covering the cabling, layouts, and media that carry your data. In this session, we'll cover the physical fabric of the network. We'll answer several questions. What shapes the quality of a transmission medium? How do the common cable types compare? Why does cable length have a limit? How is the network laid out and organized? And what underlying signaling technologies make it all work? Why does this matter beyond the exam? Because the most common cause of a network going down is not a clever attack, it is a cable. Picture a hospital wing where a run of the wrong cable, stretched too far past its limit, drops connections at random during patient care. Availability is a security property, and the physical layer is where it quietly lives or dies. Knowing your media and layouts lets you build for uptime and resilience from the ground up. What shapes the quality of a transmission medium? A handful of physical factors, and they apply whether the path is a cable or open air. Attenuation is the loss of signal strength over distance. Interference is unwanted signals, from electrical noise or radio sources disrupting yours. Noise is random variation that distorts the signal. Jitter is uneven delay between packets, and bandwidth is the range of frequencies the medium can carry, which caps how much data flows. Propagation delay is simply the time a signal takes to travel end to end. Design well, and these stay in check. Ignore them, and your data arrives late, garbled, or not at all. Think of a garden hose. Too long, too kinked, or too narrow, and the water dribbles out weak. How does coaxial cable fit in today? Mostly as a legacy and specialty medium. It has a copper core wrapped in insulation, a braided shield, and an outer sheath, which gives it decent resistance to interference. It once carried local networks widely, but was long ago overtaken by twisted pair wiring. Now you are far more likely to see it linking an antenna to a television or running from the wall to a cable modem than serving as network cable. Its classic weaknesses were bending it too sharply and breaking the core, running it past its length limit, or failing to terminate and ground it properly. Picture an old garden hose you keep around for one specific outdoor tap, not for daily use. Why is twisted pair the everyday workhorse? Because it is thin, flexible, cheap, and clever. It bundles 4 pairs of copper wires, each pair twisted at its own rate. And that twisting is the trick. It cancels out interference and reduces crosstalk, where a signal on one pair bleeds onto another. Tighter twists mean more resistance to noise and higher possible throughput. Add a foil shield and you get the shielded variety for noisy environments. Leave it off and you have the common unshielded kind. The categories climb in capability as the twists tighten and the quality improves. Its main pitfalls are using too low a category for the speed you need, or running it past its length limit. Picture braided rope. The tighter the weave, the stronger and cleaner it pulls. Why does a cable have a maximum length at all? Because the metal fights the signal. Copper is a fine, affordable conductor, but it still resists the flow of electrons, and that resistance degrades the signal over distance, the attenuation we met earlier. Each cable's rated length marks where that degradation starts to interfere with clean transmission. Push past it and you get more errors and retransmissions. And the faster the speed, the sooner attenuation bites, so shorter runs suit higher speeds. You can extend reach with repeaters that boost the signal, but there is a classic rule limiting how many repeaters and segments you can chain between two nodes on older shared networks. Think of shouting a message down a long hallway. Eventually you need someone posted partway to relay it, but too many relayers garble it. What makes fiber optic cable special? It sends light instead of electricity. That gives it remarkable speed and makes it nearly immune to tapping and interference. A real security advantage, and its cost premium has shrunk over time. It comes in two flavors. Single mode carries one light signal down a thin core with low attenuation over long distances and huge bandwidth. Multi-mode carries several signals down a wider core with more attenuation and shorter reach. A multiplexing technology lets many independent data streams share one fiber at once, each on a different wavelength of light, multiplying capacity. Picture separate colored laser beams traveling the same glass thread without ever mixing. How is the network organized beneath the cabling? Through its transport architecture, and three ideas anchor it. First, topology is the physical or logical layout of devices and links, which shapes scalability and fault tolerance. Second, network functions divide into planes. The data plane forwards user traffic. The control plane decides how that forwarding happens and maintains the tables, and the management plane handles configuration and monitoring. Separating them lets you modify one without disturbing the others. Third is a switching choice. Cut-through forwards, a frame the instant it reads the destination for low latency, while store and forward buffers the whole frame first for better error checking. Think of a mailroom that either flings each letter onward the second it sees the address, or inspects each one fully before sending it. What are the basic network topologies? There are 4 classic layouts, and each handles failure differently. A ring connects systems in a loop where a token grants the right to transmit, but a single break can halt the whole loop unless it has redundant paths. A bus ties every system to one shared backbone, so any one segment failing spares the others. Yet that central line is a single point of failure, and any disconnection can down the network. A star wires each system to a central hub or switch, so one failed segment leaves the rest working, though the hub itself is the single point of failure. And a mesh links systems through many redundant paths, surviving multiple failures at the cost of far more cabling. Picture a city's roads. A single ring road, one main street, spokes from a roundabout, or a dense grid of interconnections. Why is Ethernet the dominant local technology? Because it is a proven, shared media approach that just works. It lets many devices share one medium, but requires them to take turns and manage collisions, using broadcast and collision domains. It supports full two-way communication, usually rides twisted pair cabling, and typically deploys as a star or bus. Its data travels in units called frames, and its speed grades have climbed from fast to gigabit to 10 gigabit tiers. Ethernet is not one thing, but a bundle of supporting technologies working together. Think of a well-run town hall meeting where everyone shares one microphone but follows the rules for when to speak. What signaling technologies underpin all of this? A few fundamental choices about how bits move. Signals are either analog, a continuous wave that varies smoothly, or digital, crisp on-off pulses that resist distortion far better over distance. Communication is either synchronous, paced by a shared clock for high-speed transfer, or asynchronous, using start and stop markers, better for smaller bursts. And a medium is either baseband, carrying a single channel at a time, which is how Ethernet works, or broadband, carrying many simultaneous channels by dividing up frequencies. As with cable and fiber services, these pairings are the grammar of every link. Picture the difference between a steady drumbeat keeping a band in time and musicians cueing each other by nods. So let's bring it together. The quality of any medium comes down to physical factors like attenuation, interference, and bandwidth. Coax survives mainly as legacy and specialty cable. Twisted pair is the flexible everyday workhorse, and fiber sends light for speed and security. Cable length is capped by conductor resistance, and repeaters extend it within limits. The network is organized by topology and by separated planes, with a cut-through or store and forward switching choice. The 4 topologies trade redundancy against cost, Ethernet rules the local network, and analog versus digital, synchronous versus asynchronous, and baseband versus broadband are the underlying signaling grammar. In the final part, we cover how devices share the medium. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 11.17, Part 5. This is the 125th session of the CISSP Exam Prep series. This final part explains how a single medium gets shared without chaos. In this session, we'll cover how devices share the wire. We'll answer several questions. How many destinations can one transmission reach? How do networks decide whose turn it is to talk? How do the sensing methods differ? And how do orderly, permission-based methods keep collisions from ever happening? Why does this matter beyond the exam? Because a shared medium is a shared problem. Picture an open-plan office where everyone tries to talk at once in a meeting. No one is heard and the room descends into noise. Networks face the same challenge on a wire, and the rules they use to take turns directly shape performance and reliability. Understanding these methods helps you reason about congestion, efficiency, and why some designs stay orderly while others degrade under load. How many destinations can a single transmission reach? That depends on the casting technology, and there are 5 worth knowing. A broadcast reaches every possible recipient at once. A multicast reaches a specific chosen group. A unicast targets exactly one recipient. An anycast sends to whichever member of a group is nearest or best positioned in the network. And a geocast delivers to every device inside a defined geographic area. The distinction is simply about audience, from everyone, to a group, to one, to the nearest, to a region. Picture a speaker choosing whether to address the whole auditorium, a reserved section, one guest, the closest usher, or only the people seated in the balcony. How do networks decide whose turn it is to talk? Through media access approaches, which fall into 3 broad philosophies. Arbitration uses a central authority or a fixed set of rules to grant permission, so devices ask or wait their turn under coordination. Deconfliction avoids clashes in advance by handing each device its own dedicated time slot or frequency band. And contention lets devices simply compete for the medium, transmitting when they have something to send and dealing with collisions when they happen. The trade-off is order versus freedom. Coordinated methods prevent chaos but add overhead, while contention is simple but can get messy. Think of a meeting run by a strict chairperson versus scheduled speaking slots versus a free-for-all where people jump in. How does basic carrier sensing work? By listening before speaking. In carrier sense multiple access, a host first checks whether the medium is in use. If it is quiet, the host transmits, then waits for an acknowledgement. If no acknowledgement arrives within a timeout, it assumes the message failed and starts the whole process over. The catch is that this basic form does not actually handle collisions. It only notices failure after the fact, when the acknowledgement never comes, and then tries again. Picture someone who listens for a pause in conversation, jumps in, and only realizes they were talked over when no one responds. How does collision detection improve on that? By listening while it talks. This contention method starts the same way, sensing the medium and transmitting if it is free, but it keeps listening during transmission for signs of a collision. The moment 2 hosts clash, the sender broadcasts a jam signal telling everyone to stop. Each host then waits a random interval before trying again, which keeps them from colliding a second time in lockstep. This is the method wired Ethernet uses. It tolerates collisions but reacts quickly, though all that stopping and retrying costs a meaningful slice of throughput. Think of speakers who fall silent the instant they hear themselves overlapping, then each count to a different random number before resuming. How does collision avoidance take a different tack? By seeking permission before transmitting at all. Here a host listens, and if the medium is free, it requests permission to send rather than just sending. Only once permission is granted does it transmit, then wait for acknowledgement, starting over if none comes. Because only one device is cleared to talk at a time, collisions are largely prevented rather than merely detected. This is the approach wireless networking relies on, where you cannot reliably hear collisions in the air. Picture a classroom where students raise a hand and wait to be called on, instead of blurting out and colliding. What makes token passing collision-free? A single pass permission. In this orderly method, a digital token circulates among the systems, and only the host holding the token may transmit. When it finishes, it releases the token to the next system in line. Because exactly one device ever holds the token, two systems can never talk at once, so collisions simply cannot occur. This approach powered older, ring-based network technologies. Think of a meeting where only the person holding a single talking stick may speak, and they must hand it on before anyone else gets a turn. How does polling keep order from the top down? By having a primary system offer each device a turn. One system is designated the primary, and the rest are secondaries. The primary asks each secondary in sequence whether it needs to transmit, and grants permission when one does, then moves on to the next. It is the mirror image of collision avoidance, where the secondary asks for permission. In polling, the primary offers it. It can even weight the order to give a critical system more frequent turns. Picture a teacher going around the room, calling on each student in turn, and circling back to a key student more often. So let's bring it together. Casting technologies define reach, from broadcast to everyone, through multicast, unicast, and anycast, down to geocast within a region. Media access falls into three philosophies: arbitration, deconfliction, and contention. Trading order against freedom. Basic carrier sensing listens then hopes. Collision detection reacts to clashes and drives wired Ethernet. And collision avoidance asks permission first and drives wireless. Token passing and polling prevent collisions outright through a pass token or a primary offering turns. Choose the method to fit the medium and the shared wire stays orderly. That completes our tour of secure network components. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.